This example starts from an acetal. In finding the structures of the products of the hydrolysis of this acetal, we need to note that this carbon is the one that's in the same oxidation state as an aldehyde or a ketone. It has 2 bonds to oxygen. And so that carbon, I'm going to draw here, and that is the carbonyl carbon. And it has a phenyl group attached to it. So this is an aldehyde. The side product from that then, the other half of this molecule, is this alcohol, this diol. So the fact that there are 2 hydroxyl groups on the same molecule means we only need 1 equivalent of that molecule drawn to balance this equation. The other reactant that we need, this is a hydrolysis reaction, so here's our water as a reactant. And the hydrolysis of acetals requires a strong acid. So we will do this example using HCl as our strong acid. So in the first step, the acid is going to protonate one of these oxygens. The purpose that that serves in our mechanism is to explain why that oxygen is going to be able to be a good leaving group. So upon protonation, it is now a strong enough or good enough leaving group to get kicked out by the neutral oxygen that's attached to the same carbon. That provides a positive charge on the oxygen whose lone pair was being used, and it provides an alcohol, a hydroxyl group over here that is now detached from the carbonyl carbon. This is where our stoichiometric reactant, water, comes into play. Water can act as a weak nucleophile. This is an activated carbonyl because it has a plus charge on the oxygen. This neutralizes the plus charge and gives us a new oxygen attached to that carbon, which has a plus charge. The next step is, the next 2 steps are acid-base reactions, and we'll use the conjugate base of the original acid that we used for this. So here's the neutral structure. It's a hemiacetal, and this molecule is also an alcohol over here. By opening the ring, we've separated those 2 from each other. We've regenerated then our HCl, so it's now available to act as a strong acid over here. We're protonating this oxygen because we know that in order to explain the final products we're trying to explain, it needs to act as a leaving group. So here it is protonated with a positive charge. And now it is a good enough leaving group to get kicked out by the adjacent neutral oxygen lone pairs, coming down to form a pi bond. So there's our diol side product that's been formed. And in the last step, we'll use the chloride ion one more time to deprotonate, and that gives us the benzaldehyde and the HCl. zooming out to look at the big picture and make sure this is mapped correctly, we have a catalytic acid, HCl. So here it's being used and then regenerated, used again, and then regenerated again. So we end up with the HCl on the far right side that we used originally. We're using a stoichiometric water molecule here, one equivalent of it, and that water shows up in the mechanism here. And we have, let's see, we can map the diol side product that we got. We saw that show up right here. Okay, let's zoom back in. We're going to go in the opposite direction now. So starting from the aldehyde, and using HCl as a strong acid, we can protonate the carbonyl, which makes it a much stronger electrophile. It can now get attacked by our nucleophile. I'm going to be really lazy and not redraw that nucleophile. Here's the oxygen that was the nucleophilic site. It has a plus charge. I should make sure I draw that hydrogen out because it's going away pretty soon. From here, we're going to use our chloride ion as a very weak base. This gets us to the hemiacetal functional group at that site. And now the HCl molecule can act as a strong acid, and in the direction we're trying to explain here, we want to get rid of this OH, so that's the one that we're going to protonate. That has become a much better leaving group than it was before. And so it can get kicked out by the neutral oxygen that's nearby. This carbonyl pi bond that we've generated is highly reactive as an electrophile because the oxygen has a plus charge on it. So it is an electrophilic site for the cyclization step. This alcohol that's just been hanging out along for the ride here comes in and cyclizes. That neutralizes the oxygen plus charge down at the bottom. We still have a plus charge from the one that acted as a nucleophile just now. The chloride ion can act as a weak base to deprotonate and provide the neutral structure. And that generates an HCl molecule as the side product of that step. So if we're going to zoom out and make sure that we've mapped everything, we needed to explain the fact that the HCl was catalytic. So let's go ahead and highlight those in yellow. Starting from the right side, the beginning of the reaction that we were just drawing, we used a strong acid. We used its conjugate base. We used the strong acid again, and we used its conjugate base, and that generated the strong acid back at the end of that scheme on the far left. We have used a stoichiometric diol, which we didn't even bother to redraw a second time from the above scheme, and we need to explain where the water as a product of this reaction went. And we actually haven't drawn that in our scheme yet. We lost track of it. But here is a hydroxyl group acting as a leaving group. Ooh, excuse me. Here is a water acting as a leaving group. And let's get that highlighted in green. And let's draw it as the side product in the appropriate location. There it is once it's left as a stoichiometric side product.